We're very happy to have Alexandra Florea from UC Irvine to speak to us about simultaneous non-vanishing of L-functions at the central points. Yes, please.
Okay, thank you so much for inviting me. I'm very happy to be here. So I will talk about joint work with Bui and Bui-Milinovich about simultaneous non-vanishing of Dirichlet L-functions at the central point. So let me start with a classical question. Namely, is L of 1/2 chi equal to 0, where chi is a character mod Q? So in general, there's this philosophy that if you have an L function vanishing at a special point, usually we're looking at the center of the critical strip, it vanishes for either very deep reasons. For example, if you look at L functions associated to elliptic curves, you really expect some deep reasoning to have vanishing or non-vanishing through the BSD conjecture. Or it can vanish for trivial reasons. For example, if the root number is equal to -1, then you trivially have vanishing. Now, if you look at characters, Dirichlet characters mod Q, you don't really expect deep reasoning to have vanishing. So then there's a conjecture of Chawla. This was originally stated for quadratic characters, but you can extend it to any character, and it says that L of 1/2 chi should never vanish for any character chi mod Q. Now, proving this for every L function is very hard, so you can try to prove some statistical results. So if you look at all the family of characters mod Q, there's work of Irvine and Sarnak, who proved that SQ, the modulus of the character, gets large, more than 1/3 of the L functions don't vanish. And previously, there was some work of Murty and Murty, who also got a positive proportion of non-vanishing, but a smaller proportion. Now, this result has been slightly improved over the years by several people. The best available proportion is due to Khan, Milinovich, and Go, who got a proportion of 5/13 for Q, the modulus prime. So this is slightly bigger than 1/3. And this is the best available result for all the family of characters mod Q. Now you can also look at special families of characters, and the most natural one is the family of quadratic characters. And in this context, sound proved that more than 7/8 of quadratical functions are non-vanishing. So he looked at real primitive characters. Now, all these results here use moments, the modifier method. You can obtain stronger results in general if you compute the one-level density of zeros in the family, but those usually give conditional results. So for this family, this particular family of real primitive characters, there's work of Osluk and Snyder, conditional on DRH, and they get a proportion of 93.75% non-vanishing. So this is 87.5, this is slightly better, and this is computing the one-level density. You can, of course, look at other families of characters, for example, cubic families or fixed order characters, and the results are usually much weaker than for the family of quadratic characters. So the question I'm interested in today is that of simultaneous non-vanishing. for Dirichlet L-functions. And let me give some motivation for studying these kind of questions. So Ivanich and Sarnak proved the following results. If you look at holomorphic cusp forms of fixed weight K, and you fix two real primitive characters, chi1 and chi2, if you vary the level square free, so for n square free large enough, they prove that the positive proportion of these holomorphic cusp forms of weight K level n have a simultaneous non-vanishing property, namely have the property that L of 1/2 f twisted by chi1 non-zero and L of 1/2 f twisted by chi2 non-zero. This result has been extended over the years. One such result is due to Michel and van der Kamp, where they proved some kind of simultaneous non-vanishing result for 3 L-functions. So they showed they got a positive proportion of holomorphic cusp forms of weight 2 and prime level Q having a triple non-vanishing property, so L of 1/2 f twisted by chi j non-zero at the same time. Now it turns out these kind of questions have connections to Landau-Siegel zeros. So maybe this is the original motivating question. Now in their paper, Ivanich and Sarnak say that you can study these questions for Dirichlet functions too, but it's not clear if there are any connections to these deeper questions about zeros. So one result.
The thing we liked was we got to 50% and just needed to get a 51.
Exactly. So you just
we hit the barrier.
Exactly. So you need just to go slightly over 50% and then you're good.
What's the motivation behind Galois' picture? Why did he believe that they never vanish?
Well, I think, okay, I'm not sure what Galois' motivation was, but I think from like a modern perspective, maybe you really expect vanishing for some deep reason, like in the case of an L function associated to an elliptic curve, or for a trivial reason. And here you don't really have any of these, so why should they vanish? But I'm not sure if he had other
Is there a conjecture like this for more general, more typical functions?
I'm not sure. Yeah, I'm not sure about more general.
We could make one.
And you'd be safe.
We did make one. Then.
You did make one.
If we did make one, then maybe this product of two L functions can be viewed as a more typical.
The only point at which any human has ever said an L function vanishes at a half, there's no other value that anybody can ever say that any L function vanishes explicit.
Well, for various motives, I mean, the half of the
The centers only.
But this is the case when the half is not really a critical value.
Yeah.
Yeah, so you wouldn't
Yeah.
I'd be willing to conjecture non-zero for most things.
You're being recorded, Chris.
I doubt anyone cares what I think.
That's deep.
Okay, so the result that we're trying to extend is the following due to Zacharias. he proves non-vanishing for 3 L-functions. So he takes Q to be a prime. He starts with 3 characters, chi1, chi2, chi3, modulo Q. And then he shows that the positive proportion of characters mod Q have this triple non-vanishing property. So if you look at L of half, chi, chi, j, these are non-vanishing. So this is the result of proofs, of course, when Q goes to infinity. And we will try to increase this to 4 L-functions. But let me first describe a few of the ideas in his work. So he's also using modifiers. So what's the idea here? He starts with a classical looking modifier. So M of chi L, this is a Dirichlet polynomial of length, let's say L, which is a small power of Q. So it's chi of L, mu of L over square root of L, with this weight 1 minus log L over log capital L squared. Now with this modifier, he uses Holder, and he gets that the number of characters mod Q with this triple non-vanishing property is bigger than a cubic moment over a 4th moment. So it's a cubic moment, the sum over chi of the cubic modified moments, chi, chi, j, m of chi, chi, j, is to the 4 divided by the 4th moment, the 4th modified moment with absolute value L of 1/2 chi, m of chi to the 4, this to the 3rd. So what's the point of introducing these modifiers? Well, the point is that if you don't have modifiers, so if you didn't have that here, these grow at different rates. This is like a Q log Q to the 4. This without the modifier, it would be like Q. So you get a 1 over some power of log. And when Q goes to infinity, you get an infinite family for which you have non-vanishing, but the proportion goes to 0. So the idea is to introduce these modifiers, which behave kind of like 1 over your L function, or you think of it in this way. And then the point is that these moments grow at the same rate. So what he does is he gets an asymptotic formula for this cubic moment. He shows that this is of size cube. And he also computes this 4th moment. It's also of size cube. And this is how you get your positive proportion of non-vanishing. Now, the ideas to prove these kind of results are quite different. So this 4th moment here is quite similar to the 4th moment. So ideas go back to work of Young, who did the 4th moment without the modifier, and then work of Bloomer, Uri, Kowalski, Michel, and Milinovich. Once you do that, you get an asymptotic formula with an actual constant here, and then you need to compute this cubic moment. I will just say maybe a few words about this. Here, the main difficulty is dealing with the dual term after doing the approximate functional equation. Here you have characters chi, chi1, chi, chi2, chi, chi3, so you have to deal with the root numbers, and that's not easy to do. So let's renormalize these and call them chi, chi1, and chi, chi2. Then the main difficulty is dealing with the oscillations of the root numbers. So let's say epsilon of chi 1, epsilon of chi 2, and you twist by some character chi of m. This is related to a Hyperklusterman sum. And then, so let me quickly define the Hyperklusterman sum. For there, this is the sum over A, B, C, mod Q. This product is equal to L bar. Note that A, 1 of B, by 2 of C, E of A, B, C over Q. Sorry, A plus B plus C over Q. And then the most difficult part, the critical kind of range sum that you need to deal with, is a sum of this form. So you sum over a parameter, let's call it n of size roughly q, and then you have something that looks like a divisor function. It's the convolution of 1 and this character chi 2, and then you have the Hyperklusterman sum. So you roughly need to bound expressions of this form. Now when chi 2 is equal to 1, so if you have the divisor function, this is work of Kowalski, Michel, and Sawin. So essentially what Zacharias did was extend this kind of bound for more general functions here. And this is using some deep algebraic geometry. Okay, so this is all I wanted to say about this result. Now, what it will do. So,
Sorry, what is N1 there?
so N1, well, think of it as fixed. You have 3 L functions. So you have, if you use the approximate functional equation, you have a sum over 3 variables N0, N1, and 2, which go up to q to the 3/2 roughly. So think of N1 as being outside and you want to get a bound in terms of N1. And you glue together 2 variables N0 and 2 and think of N1 as just being outside.
So is there a dependence on N in the Klusterman sum or?
Oh, there should be. Maybe it's M, N. Oh, M, N. Yeah, thank you. There should be a dependency on it. Okay, so the question is, can we prove something about more than 3 L functions? So we prove a conditional result with Hank, Bui, and Milinovich. So we assume GRH. We take Q to be prime. And we take chi 1 up to chi 4 to be primitive characters modulo DI. And here we take the DI to be less than some small power of Q. Have 1 over 3072. For simplicity, we assume that the DI are square free and pairwise co-prime. And then we get our non-vanishing result. So we get that the positive proportion of characters mod Q have this quadruple non-vanishing. So one remark about this positive proportion of non-vanishing, we don't actually.
Sorry, you're using GRH to compute level densities, or you're using it to some other?
No, we do moments.
Oh.
Yeah, but we at some point we need to have.
In fact, you're probably proving that the L's are bigger than some.
Yeah, we can get exactly.
Non-vanishing.
Yeah, exactly. We can prove something like some kind of lower bound for these, maybe 1 over log or. We use GRH because we need sharp bounds for moments of L functions, for high moments of L.
Use density?
If you use density.
Like several,
Right, I don't think that would be enough to give you this quadruple result. So yeah, there's the 50% non-vanishing on GRH due to, I think, Murty, and then there's some recent work of Carneiro, Milinovich, and someone else. But if you do the same thing, you can't do 4 functions. So in terms of the actual proportion that you get, you could write down the proportion in principle. It would be quite tedious, and the proportion is going to be really small. So for us, one key ingredient is getting sharp bounds for modified moments of L functions. That's conditional on GRH. And we follow this method of Harper, who proved sharp bounds for moments of the Riemann zeta function. But the implicit constant in there is like a double exponential. So our proportion will be like 1 over a double exponential, so really small. This kind of result of Zacharias, he doesn't write down what the proportion is, but if you could do that, it's like a reasonable number. Maybe like 5%, which seems like really big compared to the kind of thing that we would get here. So what's the strategy of this? So we also do modified moments, but they will be quite different from what Zacharias is doing. So let's assume that we have a modifier. I won't tell you right now what the modifier is, but it will be quite different from the classical one that Zacharias has. Then if you use Holder, you get that the proportion of non-vanishing for these 4 L functions times a 6th moment. This is bigger than something that looks like a 4th moment. So we have Lm of chi-chi1, chi-chi2. And then very importantly, we don't want to do chi-chi3. We want to do chi-chi3 bar and chi-chi4 bar. Okay, so then you can try to do the same thing as before. Ideally, you would want to have an asymptotic formula for this right-hand side, and then you would want to have an asymptotic formula for this kind of moment. But this is hopeless. So this is the 6th moment of Dirichlet L-functions when you're only averaging over characters mod Q. And this is beyond what we know. So the 4th moment is due to Matt Young and the 5 authors that I mentioned there. You can do the 6th moment if you do an extra average over little q going up to big Q. This was work of Conry, Vaniech, and Sam. They had an extra average there over a vertical line. And recently that was removed by Chandili, Matomaki, and Radziwill. But in any case, they also need to sum over little q. So just computing this moment is out of reach. So we cannot do that. But the point is, if you just want a lower bound for this, you don't necessarily need asymptotic formulas for this. It's enough to get a lower bound for this fourth moment and an upper bound for this sixth moment. And this is what we do. So we show that this sixth moment under GRH is bounded above, it's of size Q. And for this one, we get a lower bound also of size Q. So this is unconditional. This is conditional on GRH. This is the only place where we use GRH.
Using it for all of them.
Sorry?
You're using it for all the L functions.
We use it for all of the L functions, exactly. So here there are three main things to do. So one is that we want to define the modifier. We want to define a modifier which allows us to get this sharp bound for the modified sixth moment. And once we have the modifier, we want to prove sharp bounds.
The lower bound is the absolute value in the inside or the outside?
Over here,
Are you summing L's to absolute value, or are you summing L's and then you take, where's
so
it?
that one is with absolute value in the L function.
Inside.
This is without absolute value. So here the absolute value is outside. So really what I'm doing is L of half chi chi 1, L half chi chi 2, chi chi 3 bar, chi chi 4 bar. This looks like something with absolute value, because if the chi i's, for example, are just trivial, then you recover L with absolute value to the 4. So that was that's one of the main points. Like, we didn't want to have L of chi chi 3 and L of chi chi 4 because, yeah, that's not like a moment with absolute value. We don't know how to compute that. So we really need the bars on the character to make it look like you have absolute value inside. Okay, so we want to do sharp bounds for modified moments. And then with the modifier we define here, we want to get lower bounds for the modified fourth moment. And this is roughly equivalent to saying that we want to compute a twisted fourth moment. So these first two here go hand in hand. If you know that you want to get sharp bounds for modified moments, that kind of gives you a hint on how to define the modifier. So they kind of go together, and this is where we use GRH. And once you have the modifier, we prove the lower bound, and that's unconditional. Okay, so I have until 4:30. Or so let me tell you how we choose the modifier. So here the ideas go back to work of Sound, who got sharp bounds for moments of almost sharp bounds for moments of zeta, conditional on GRH, work of Harper, work of Lester and Radziwill. We start, so on GRH, we start with an inequality for log of L. This exact form was written by Chandi. So log of the L function is bounded by roughly a sum over the primes, prime powers. So here we have von Mangold, I of n over roughly square root of n log n. We have a weight here. And then a term log q over log x, and then an error term. Here lambda is the solution to, unique solution to this equation. It's slightly less than 1/2. So the point is that we bound log of the absolute value of the L function roughly by a sum over the primes, and we have flexibility in where we truncate the sum over the primes. So think of primes p going up to x. We can ignore the prime powers where they stop. And then you have this extra log q over log x term. This is similar to the work of sound, where he was bounding log of the zeta function. Now, once you have this inequality, if you exponentiate, you would get that L of 1/2 chi. Well, roughly, I will write this in quotes, it's roughly bounded by, the important part is the exponential of this sum over the primes. So, and for simplicity, I will just write the sum over the primes as chi of p over square root of p. Okay, I mean, I'm ignoring this weight here. Now we want to approximate this exponential by series, Taylor series. And the thing that we use is that if we want to approximate e to the t, let's say that t is of size roughly h. So let's say t is bounded by h over e squared and h is even. Then essentially e to the t is going to be bounded by a truncated Taylor series of length h. Okay, so if you use this kind of bound for the exponential of the sum over the primes, you end up with a Dirichlet series, and it's much easier now to deal with Dirichlet series. So if you do that, you roughly get, this leads to sums of the form. So now you have a sum over integers n. Here I truncated h, so I will sum over integers n. First of all, the primes of n must be less than x, the primes which divide n. And because I truncated h, I'm looking at integers n with at most h primes. So this is the number of primes with multiplicity. And then we roughly have chi of n over square root of n. And we have this combinatorial function, nu of n, which is a multiplicative function. This is just keeping track of repetitions. So prime powers, it's 1 over, up to the a is 1 over a factorial. So it's 1 on the primes. So we roughly bound the L function by this kind of expression. And then you can think of, well, maybe we can now define our modifier in a natural way. So just keep the Dirichlet series as it is and throw in a Mobius function or a Liouville function to get cancellation between the L function and the modifier. So the question is that maybe you should define your modifier m of chi as a sum over n with these same properties. And you throw in either Mobius or Liouville. On the primes, this is -1, so technically this should give some cancellation. Now the problem is that if you define your modifier in this way and you do this argument of Sound and Harper for upper bounds for moments, you don't get a sharp bound. So you get for the modified moment q times some power of log. And for us, it's really important to get q, not q times something which is going to infinity.
Can't optimize?
Sorry, no, you can't optimize. So even with like optimal choices of H here, it's not going to give you a sharp bound. It's kind of the same as in Sound's work on moments of the Riemann zeta function. What Sound was doing was he bounds log of zeta by a sum over the primes. If you just do the moments of the sum over the primes, that's not going to give you an optimal bound. So Sound split his sum over primes into two intervals. And then for the short sum, you can compute more moments. The bigger primes have a smaller contribution, like you can compute fewer moments, but that contribution is going to be smaller. So then if you do kind of the same thing, split your primes into two intervals chosen appropriately, you still don't get a sharp bound. So you have to do Harper's argument where you split the primes into infinitely many intervals and work on one interval at a time. So this is what we do. Split the primes into roughly log intervals. Let's say beta j is like e times beta j minus 1, and beta naught is like log over log. It's not very important for the purpose of the talk, the actual value of beta. And we stop when beta k is small. Let's say beta k is epsilon. So we only work with primes up to q to the epsilon. And then we modify on each of these subintervals. So mj of chi will be a sum over integers whose primes are in the jth interval and which have at most, let's say, hj primes. You have to choose these parameters appropriately. And then you define it in this kind of natural way as mu of n, chi of n, mu of n over square root of n. And then you take your modifier to be the product of these species. And now,
Can you explain? I mean, I haven't seen these complicated modifications, but usually there's a weight which, like a C1 sum with a 1 minus log n over the parameter, which of course does optimally in the setting we were doing. That's a trivial gain. It's never. I mean,
so for us, the problem is that when you do upper bounds for moments, the upper bound for the kth moment is something like e to the big O of k. And roughly because you have to split your primes into infinitely many intervals, you cannot, this technique is never going to give you better than e to the big O of k. The best you can do with this technique is improving the big O of k, the constant in the big O of k.
so, you just guess it's of the form. You just put mu of n in there?
Well, you put mu because on the primes it's -1. So
Okay, I know that mu's supposed to be there, but
sorry?
I'm just saying, so that's all you do. You just
Yeah, pretty much. If you think of the L function as like 1 plus chi over something, then this is like 1 minus. So when you put together, you have to deal with this kind of conditions on the number of prime factors. You don't want these to be too large because what we do is we compute moments of these. So there's restrictions on how long the polynomials can be. But you can optimize, the choice of these parameters, the choice of these betas, and the various constants in here, but that's never going to give you something like even 1%. So once we choose these beta j's, hj's appropriately, we get this sharp bound of L of m to the k, let's say, is bounded by k. So we get sharp bounds for all the moments. We just need the sixth one, but this works for all the moments.
K in the index for the intervals is the same as the moment that you're.
No, sorry. That one is capital K, the moment is little k. No, the capital K is of size roughly log Q. Yeah, capital K goes to infinity. Okay, so that's the point where we use GRH, because we start with the inequality for log of the L function, and that assumes GRH. Okay, so once we have this modifier, we need to get the lower bound for the fourth moment, which is related to getting an asymptotic formula for the twisted moment. Twisted fourth moment. So here we're looking at the sum of chi over q, and we have L of chi 1, L of half chi 2, L of half chi 3 bar, and L of half chi 4 bar, times chi of L1 chi bar of L2. So we need asymptotic formulas for things like that. Now, many of the ideas here go back to work of Young, who computed L of half chi to the 4, summing over chi mod q, and he got that this is q times a polynomial in log q of degree 4, and then q to the 1 minus 5 over 512. Now the error term was improved by Bloomer, Uri, Kowalski, Michel, and Milinovich. We got an error term of size q to the 1 minus 1 over 20. And then Bob Hoff computed twisted moments for L1 and L2 co-prime and square free. And Zachariah computed modified moments. So the main input in his work is doing these twisted moments. I should say here with the chi I right now. Zachariah did modified moments, which amount to doing this twisted moment, and he did it for L1 and L2 Q3. Again, when we don't have the chi I's. So just genuine fourth moment.
L1, L2, do you need to put?
Sorry?
Can you assume, I don't know, cube free of L1, L2 being?
No, we can't assume that because of the way our modifier is. So if you look here, actually, we have lots of prime factors. So there's no way we can get away with free. So we need to extend their work when these characters chi 1 through chi 4 are not trivial, and removing the coprimality conditions and the square free or cube free condition. So what are some ideas in doing this? Well, we start as usual with the approximate functional equation. Let's call this star here. So this is going to be a sum over chi, a sum over variables m and n. Now, instead of the divisor function that you would get in Young's work, we get these convolutions of characters. And we have, let's say, a test function V of Mn over Q hat squared. So here Q hat is roughly Q times D. So D is the maximum of the Di. So it's a longer sum over M and N. And then we have a dual term. And the nice thing about the dual term is that it's very similar to this principal piece. So it's some factor epsilon. This is just something which depends on the chi1, chi2, chi3, chi4. Doesn't depend on chi. It has absolute value 1. And then we have the sum over chi of d1, d2, d3, d4 bar times almost the same thing. But now we have chi1 conjugate, chi2. Okay, so this weight function ensures that Mn goes up to roughly Q hat squared, so roughly QD squared. And this second piece here, really, really similar to the principal piece, except that we multiply by chi of D1, D2, D3, D4 bar. So once we know how to deal with this, this is kind of automatic. So this is one reason why we started with the chi1, chi2, chi3 bar, chi4 bar. We don't have oscillations of the root number. We wouldn't know how to deal with those. So we just did the simpler moment. So Zacharias, in his work, he actually had 3 L-functions without any kind of absolute value or bar on the character. So he really had to deal with these oscillations. Okay, so we use orthogonality for the sum over characters, chi, and then we get a diagonal term. Well, we get that L1m is congruent to plus or minus L2n mod q, so we get a diagonal when L1m is equal to L2n. This is the easy term, and we get that this diagonal is equal to q over square root of L1, L2. Then we have some factors, some Euler factors. It's a product over P dividing L1. It doesn't matter what it is for now. And then interestingly, we get a product of 4 L functions. So we get L of 1, chi1, chi3 bar, L of 1, chi1, chi4 bar, L of 1, chi2, chi3 bar, and L of 1, chi2, chi4 bar. So we get the product of these 4 L functions. Okay, so now I just want to explain why when we modify, we get something of constant size. So this kind of result is unconditional, but to get a lower bound of the right order of magnitude, we actually also assume GRH. So let me remind you, M of chi I is a product with a little k from 0 to capital K of the kth piece of the modifier. And this is the product of the following. So now we're summing the kth piece, only has primes in the kth interval. Let's ignore these conditions on the number of primes. We have the Mobius function, then the character chi I, this arithmetic divided by square root of fk. So when we multiply these 4 modifiers out and multiply what we get by this main term, by this diagonal term, we get the following. So I sum over characters and I have this product of the L function and the modifier. So this will give me the product of the 4 L functions evaluated at 1 diagonal. Times this mass which comes from the modifier, but it's actually not too bad. You can remove these conditions on the number of primes. Eventually you can write it down as an Euler product. So it's really not bad. So we have a sum over M and N. M is written as a product between M naught with Mk, so that each of these only has prime divisors in the jth interval and has the same property. And we have the Mobius function mu m, mu n, square root of mn. And then we multiply, so each mj here, we combine, we write it as a product of 2 things, which comes from chi1 and chi2. So we will have a chi1 of mj1, chi2 of mj2, and then a chi3 bar nj1, chi4 bar nj2. The point is, if you remove all these conditions on the number of primes and so on, this one, because of the Mobius function, so on the primes, this is just chi1 plus chi2 and chi3 bar plus chi4 bar. So we get exactly the product over P, let's say less than Q to the epsilon. That's where we stopped in our modifier. And now we will have 1 minus, because we have Mobius, and we get chi1, chi3 bar over P and the rest. Okay, so essentially we multiply the L function evaluated at 1 of chi1, chi3 bar by this Euler product truncated at Q to the epsilon of 1 minus chi1, chi3 bar over P. So here, to get a lower bound, we have to assume GRH, which would give us that we can approximate the L function by an Euler product over primes truncated at Q to the epsilon. And then when you combine these 2 things, you get rid of the term with P. You just get terms of size 1 over P squared in the Euler product, and that's a convergence. So under GRH, we can approximate the L function by this truncated Euler product, and we get something like 1 minus chi1, chi3 bar squared of P over P squared, and then lower order terms. So these things are convergent. So we will get our lower bound for the diagonal of size Q. Now there's actually, you have to be a little more careful, because we actually have lower order terms, not just the diagonal. So in fact, we have 6 main terms in total. But the point is that when you modify the remaining 5 terms, you get something which is little o of Q. So those lower order terms in the twisted moment computation, when you modify them, they won't give you anything. So it cannot happen, for example, that you have cancellation between these 6 main terms, because the other ones are negligible. So there are 5 remaining main terms in the twisted moment, but they get modified to give little o of Q. so they are negligible. And now we need to deal with the off-diagonal terms. And here we pretty much follow Young and Blumer, Fourie, Kowalski, Michel, and Milinovich. There are some extra technical things that we need to deal with. So here, the off-diagonal term. Let's localize the two variables, little m and n, is having size capital M and capital N. So this is roughly Q over square root of Mn. And then we have a sum over little m and n with this congruence condition. We have the convolution of characters. And then some weight function. So roughly I'm summing over m of size capital M and of size capital N with the condition that Mn goes up to Q hat squared. And here we have the balanced and the unbalanced range. So in the unbalanced range,
What is Q hat here?
Q hat is Q times D, where D is the maximum of the DI. Yeah, so we the product of DMN, if D has some size, will be bigger than in the original paper of Young. So here in the unbalanced range, we pretty much follow what Young did. So let's assume that N is bigger than M. Then we have to prove some version of Voronoi summation. We couldn't find it in the literature for these convolutions of characters. So we do Voronoi summation on N. We get some dual parameter H. We glue together M and H. We use Cauchy-Schwarz. And then we use bounds for exponential sums. I should say here that originally we tried to use the approach of Blumer, Fourie, Kowalski, Michel, and Milinovich, which in the case of the fourth moment there gives better bounds. But for us, actually, the kind of results in algebraic geometry that we need, we couldn't find strong enough results. So we need to bound some bilinear forms with Kloosterman sums twisted by characters. And we used results of Michel, Kowalski, and Sawin, which end up giving actually weaker bounds than if we use these more less sophisticated tools, let's say. And then in the balanced range, when the variables are close together, we use the five-author approach. So we use the delta method, start with the delta methods of Friedlander and Ivanich. We have a sum over M and N, roughly things of this form. And then some exponential. And some parameter L, which comes from the delta method. Let's K of L here. We use Voronoi summation twice on both variables, on M and N. So this is quite similar previous work. The only thing that I wanted to say is that when we use Voronoi summation, so when we have something like this, G function is some weight function, we get on the dual side a term which only appears if D1, the modulus of chi1 divides this L. And then we have a term which involves L of 1, chi1 bar, chi2. We get another term which only exists if D2 divides L. And we have L of 1, chi1, chi2 bar. And then we have a dual sum, what you would expect from Voronoi. The point is, when we multiply these 4 terms, we get 4 extra main terms. So I mentioned slightly before when we were doing the modification that we have 6 main terms. 1 comes from the diagonal, and we get 4 more from here, and then there's another one. So I'll just end in 2 minutes. I'll just say that these terms are what we call one-swap terms. And this is not in the recipe language of Conry, Farber, Keating, Rubinstein, and Snaith, but in the sense that I swap characters with each other. So if you remember, in the diagonal case, we had L of 1, chi1, chi3 bar, L of 1, chi1, chi4 bar, L of 1, chi2, chi3 bar, and L of 1, chi2, chi4 bar. These one swap terms mean that I swap chi1 and chi3 in here, and I get various other values of L functions. We have 4 such terms. We swap chi1, chi3, chi1, chi4, chi2, chi3, and chi2, chi4. So this will give 4 one swap terms. And then in the dual term, after doing the approximate functional equation, we have a 2-swap term, which comes from swapping chi1, chi3, and chi2, chi4. And then the off-diagonal terms are bounded similarly as in the work of Young or Bruno, Fourie, Kowalski, Michel, and Nietzsche. So I'll stop here. Thank you.
Are there any questions for the speaker?
So when you go off diagonal, I mean, these, what you're calling balanced, use the delta method.
Mm-hmm.
If you were doing something unconditional, so you get this position, because this is what happened to us when we couldn't get from 50% to over, is we went to the off diagonal here, and then you get Klosterman sums, and there are some small moduli Klosterman sums that normally you would open up and just deal with Voronoi summation, and those usually are trivial, but if you're trying to give an effective lower bound, which is, so we were able to get 51%, but then assuming that, I mean, ineffectively. So the thing kind of blew up in our face. So I'm just trying to understand here, don't you get when you're doing this delta method, I think we call it determinant method there, don't you get small moduli where you're opening things up? I mean, I know you're assuming Riemann through it. Yeah.
So here, actually here we're not assuming Riemann. So
yeah, but then I'm trying to understand. And you also had this lower bound for L1 chi. Can you say? Can you go back and state the main theorem? That may help me. Those are not fixed or they're variable. You sum over Q, but the estimate is supposed to be uniform in chi1, chi2, chi3.
Yes. So, okay, for the twisted asymptotic, so just for L chi chi1, chi chi2, chi chi3 bar, chi chi4 bar, times some twist chi of L1, chi bar of L2, we don't use Riemann. We use Riemann when we modify. So after we introduce the modifier, from all these terms like diagonal and these one swap and two swap and so on, we get these L functions. And then from the modifier, you have this small Euler product. And we want to show that the L function and the Euler product modifier interact with each other and you get something bounded. And if we don't assume GRH, we don't know how to do that because we want to approximate these L functions evaluated at 1 by short Euler products. So that's one point where we use GRH, and then of course we use GRH in the upper bound part. But just for the twisted asymptotic, we don't use GRH.
So in your main results, you have these characters to modulate D sub I, where the D sub I are pairwise co-prime. Is there any potential for handling characters which are not so independent? For example, maybe chi4 is chi1, chi2, chi3. So,
okay, that would be a different moment computation, I think. So what I will say is that it shouldn't be impossible to remove the, all these like coprimality and like square free conditions. Those we mostly assumed for the purpose of Voronoi summation, which is anyway quite complicated when you have these convolutions and not just the divisor sum. But if you actually have the chi4 being dependent on chi1, chi2, and chi3, I'm not sure exactly what you would get.
So I'll just make a comment. It will be clear from the comment that I'm not an analytic network theorist. So for zeta functions of smooth projective varieties over finite fields, there is a motivic interpretation of the order of vanishing that s equals 1/2 of the zeta function. This is essentially due to Tate. It's the rank of a homomorphism of the set of homomorphisms of the group of homomorphisms between the supersingular elliptic curve and the Picard variety of the variety in question. So from that, you can tell right away whether the zeta function vanishes, what order of vanishing you've got, and so on. That has been extended to L functions. So twists with characters and so on. It's the same type of motivic interpretation. At some point, Manin asked for a motivic interpretation of the order of vanishing of the Dedekind zeta function of a number field at 1/2. Does that exist anywhere in the literature? Has it been achieved?
Well, for those, the expectation is you never vanish except for the root number built into the goal, like. Yeah, you can make a Dedekind zeta function vanish at 1/2 with the functional equation even, but that's because you haven't broken up it into the irreducible representation. The others should never vanish. You can extend Charlotte to say that.
What Manin was actually asking for was construct the square root of the Tate motive, Z of 1, and make the homomorphisms of the Tate motive into the Dedekind motive.
That's what the supersingular elliptic curve.
Well,
that's right.
That's the characteristic. So that's the supersingular elliptic curve in characteristic P.
Z of 1/2.
Yeah, but Z of 1/2 for number fields does not exist.
Well, I think the standard conjecture is that you only vanish for the reasons of symmetry, which may be built into the fact that the Dedekind zeta function might, factors into cuspidal L functions. Then, but that particular parameter, 1/4. So the gamma factors are S over 2, or for those, nobody's expecting any vanishing like BSD does. At least that's the way I understand it. I think Sarah's thought about it, maybe even written it somewhere.
So this modifier you're using, it's more efficient in this context, I guess, than other modifiers. But is it the reason that it's more efficient because you're using GRH?
It's more efficient in the sense that it gives us the sharp bounds.
Yeah, but like a lot of like you can use kind of similar modifiers on different moments of L-functions problems, right? Like you could look at other non-vanishing problems and say, I'm going to try to use the same modifier. And would that only, like, if I had some different moment of L-function problems, would it only work to use the same modifier if I assume GRH? Or is there a chance that it could work on a different, like, non-vanishing problem where we don't have to assume GRH?
Sorry, so the question is if you can use this without GRH or?
Yeah.
Well, I mean, it's GRH is kind of embedded in the way we choose the modifier, because the motivating thing to choose your modifier is exactly the way you bound this log of L function by a sum of the primes, and then this whole argument machinery for upper bounds for moments. So in some sense, this type of modifier is helpful in other contexts where maybe. So there are instances where, for example, you can't get like positive proportions of non-vanishing if you use the one level density approach, which is usually better than doing modified moments. But if you do this kind of modifier, then you can get positive proportions with like terrible proportions of non-vanishing, but positive. So it's helpful in certain situations. So for example, for cubic L functions, if you look at L functions associated to cubic characters, if you do the one level density of zeros, well, you expect that to give something better than just doing moments, but it actually fails to give a positive proportion. So you need, in the one level density approach, you need to go beyond -1, 1, and at least with the current techniques, we can do that. But then if you notice that you don't actually need to compute a modified second moment and a modified first moment, it's enough to get a sharp bound for a modified second moment, then you can use this construction. And on GRH, you can get a positive proportion. So it's helpful when you can't quite compute a moment, but you hope to get a sharp bound. And that would be enough.
I have a historical comment. If Solberg was sitting here in the audience and you were giving this lecture, he would not like the word modifier. He was very allergic to that. That was invented by Levinson.
It's too soft for him.
No. He invented it, but he didn't like the word for some reason, just because Levinson explained it very clearly. He was very upset when people called it a modifier.
Or did he have a suggested name?
I read his paper, I don't know. And even he invented it when he did the positive portion of zeros. No. You'd say that and he'd get quite irritated. I took a trip with him to China and he kept on getting irritated when people said modifier.
Okay, are there more questions? If not, let's thank you.